You think light fades. You turn on a flashlight, and the beam gets dimmer with distance. You look at distant stars, and they're faint. So obviously, light weakens as it travels, right? It gets tired, uses itself up, disappears into the darkness. That's what everyone assumes. But here's what bothers me about that picture. Light doesn't get tired. A photon that left a star 1 billion years ago hits your eye with exactly the same energy it had when it started. Light doesn't decay. Light doesn't fade. Light never dies. So if light never dies, why isn't everything blindingly bright? That's the question that should be keeping you up at night. Every star is pouring out light constantly. That light travels forever through space. It never stops, never slows down, never loses energy. The universe is 13 billion years old. That's 13 billion years of starlight, filling up space with photons that never go away. Where is all that light? Why can you see darkness at all? Let's start with what actually happens when you turn on a light. Say you've got a light bulb. It's emitting photons in all directions, trillions and trillions of them every second. Each photon shoots out in a straight line at the speed of light. Now here's the critical thing. That photon keeps going until something stops it. It doesn't fade. It doesn't lose energy just from traveling. If there's nothing in the way, it goes forever. The photon that leaves the bulb has the same energy whether it's traveled 1 meter or 1 billion meters. But you say the light looks dimmer far away. That's true. You're right about that. Stand close to the bulb. It's bright. Stand far away. It's dim. So something is happening with distance, but it's not that the photons are weakening. Here's what's really going on. The photons are spreading out. The bulb emits light in all directions. Imagine a sphere expanding around the bulb, getting bigger and bigger. All those photons are distributed over the surface of that sphere. The farther you go, the bigger the sphere, the more spread out the photons become. Think about it this way. Close to the bulb, maybe 1 million photons per second hit your eye. Step back twice as far, and now those same photons are spread over 4 times the area. Only 250,000 hit your eye. Step back 10 times as far. Spread over 100 times the area, only 10,000 photons reach you. The photons themselves haven't changed. Each one still carries the same energy, but there are fewer of them hitting your eye per second. That's why it looks dimmer. It's a geometric effect, not a physical weakening of the light itself. This is why we have that inverse square law for light intensity. Double the distance, the light spreads over 4 times the area, you get 1/4 the intensity. Not because photons are dying, but because they're diluting. The total amount of light energy is still there, exactly the same, just distributed over a larger and larger sphere. Every photon that left the bulb is still out there somewhere, still traveling, still carrying its energy. They just went in different directions. Now let's push this to an extreme. Take the sun. It's been burning for 4.5 billion years, pouring out photons constantly. Those photons are traveling outward in all directions at the speed of light. The ones that left the sun 1 million years ago are now 1 million light years away, still traveling. The ones that left 1 billion years ago are 1 billion light years out. None of them stopped. None of them disappeared. They're all still there, filling up space with sunlight that will never die. Multiply that by every star in the galaxy. Hundreds of billions of stars, each one pumping out light constantly for billions of years. All those photons spreading out, traveling forever, filling the universe. Then multiply by every galaxy. Hundreds of billions of galaxies, each with hundreds of billions of stars. The amount of light that's been emitted and is still traveling through space is staggering, absolutely staggering. So why isn't space blazingly bright? Here's where it gets interesting. Most of those photons are traveling through empty space, and in empty space, there's nothing to stop them. A photon will just keep going in a straight line forever unless it hits something. So all that ancient starlight is out there, but most of it isn't hitting anything. It's just traveling through the void. The photons from distant galaxies are passing through your location right now, but most of them miss you. They go right past your eye without interacting. The ones that do hit you, you see, that's what you call starlight. But think about what that means. You look up at night, you see stars. Each photon that hits your retina traveled maybe hundreds or thousands of years to reach you. It left some star long before you were born, traveled through space, happened to be aimed in exactly the right direction to hit your eyeball, and triggered a chemical reaction in your retina. That's an incredibly unlikely event for any particular photon. Most photons miss you entirely. So the darkness, you see, isn't absence of light. It's the absence of light hitting your eye. The space between stars isn't empty of photons. It's full of photons, unimaginably full. But they're all traveling in different directions, most of them not toward you. You're swimming in an ocean of light that mostly misses you. When you look at the dark sky, you're seeing all the directions where no photon happened to be aimed at your eye at that moment. But wait, there's more to it. Even if a photon is aimed at you, it might hit something else first. Dust, gas, planets, other stars. Space isn't completely empty. There's stuff out there, and when light hits stuff, it gets absorbed or scattered. That photon that was traveling toward you might get absorbed by a dust grain 1,000 light years away. You never see it. The energy gets converted to heat in the dust. The photon is gone, but the energy isn't lost, just transformed. This is crucial. Photons don't die of old age, but they do get destroyed when they hit matter. Every photon eventually hits something. Maybe it takes a microsecond, maybe it takes 1 billion years, but eventually it collides with an atom, gets absorbed, and its energy goes into heating that atom or causing a chemical reaction or ejecting an electron. The photon itself ceases to exist. Its energy remains, but the photon as a traveling particle of light is finished. So there's a balance. Stars create photons constantly. Those photons travel until they hit something. When they hit something, they're absorbed. The universe isn't filling up with light indefinitely because photons that were created billions of years ago have mostly hit something by now. The distant photons are absorbed by distant matter. Only the photons that happen to travel through empty space and happen to be aimed at your eye make it to you. And there aren't that many of those. Now here's something that will bother you. If you look in any direction in space, if you look far enough, you should eventually see a star. There are so many stars that every line of sight should terminate on a star's surface. That means the entire sky should be as bright as the surface of a star. This is called Olbers' paradox, and it puzzled people for centuries. If the universe is infinite and eternal and full of stars, why is the night sky dark? The answer is the universe isn't eternal. It had a beginning. The Big Bang happened 13.8 billion years ago, and before that there were no stars. So when you look at very distant regions, you're looking back in time, and eventually you're looking at a time before stars existed. There's a limit to how much light has had time to reach us. The universe is big, but it's not infinitely old, and light travels fast, but not infinitely fast. Most of the universe is too far away for its light to have reached us yet. Also, the universe is expanding. When light travels from a very distant galaxy, the space between that galaxy and us is stretching. The photon's wavelength gets stretched too. It redshifts. A photon that started out as visible light might arrive as infrared or even radio wave. The energy decreases, not because the photon is tired, but because the space it's traveling through is expanding. By the time very distant light reaches us, it's shifted to wavelengths we can't see with our eyes. So that's why the night sky is dark. Not because light dies, but because 1, most photons miss us, 2, many photons get absorbed before reaching us, 3, the universe hasn't been around long enough for light from very distant regions to arrive, and 4, Light from the most distant regions is redshifted beyond what we can see. The darkness is a consequence of geometry, absorption, cosmic age, and expansion, not photon death. But let's come back to Earth. You're in a room right now. The lights are on. Photons are bouncing everywhere. They hit the walls, get absorbed or reflected. If they're reflected, they bounce off in another direction, maybe hit another wall. Eventually, every photon gets absorbed. The walls heat up very slightly. The photon's energy becomes thermal energy, random jiggling of atoms. The photon is gone, but the room doesn't fill up with light indefinitely because photons are being absorbed as fast as they're being created. Turn off the light. What happens? The bulb stops creating photons. The photons that are already in the room keep bouncing around for a tiny fraction of a second. Then they all get absorbed by the walls. Within nanoseconds, the room is dark, not because the photons faded away, but because they all crashed into matter and got absorbed. If your walls were perfect mirrors, the room would stay bright forever, the photons just bouncing around eternally. But there are no perfect mirrors. Every surface absorbs a little bit of light with each bounce. Here's something beautiful about this. Every time you see anything, you're catching photons that were emitted or reflected by that thing. When you look at a tree, photons from the sun bounced off the leaves and happened to travel in the exact direction of your eye. When you look at the moon, photons from the sun bounced off the lunar surface and traveled 240,000 miles to hit your retina. The photon that lets you see the moon left the sun 8 minutes ago, bounced off the moon 1 second ago, and just now hit your eye. And that photon, from the moment it left the sun until the moment it hit your retina, didn't change. It traveled through space, bounced off the moon, traveled through Earth's atmosphere, passed through your cornea and lens, and finally got absorbed by a molecule in your retina. Same photon, same energy, doing exactly what photons do, traveling in straight lines at the speed of light until something stops them. It didn't slow down, didn't get tired, didn't fade. It just traveled until it got absorbed. Now think about the photons that miss your eye. There's a tree in front of you. Sunlight is hitting it. Billions of photons per second are bouncing off in all directions. Your eye is tiny, maybe half a centimeter across. Out of all those billions of photons, only a few thousand happen to be aimed at your eye. The rest scatter in other directions. They might hit the ground, or another tree, or the sky. They might travel for miles before hitting something. Each one is carrying information about the tree. But only the ones that hit your eye let you see the tree. This is why you can't see around corners. Light travels in straight lines. If there's something blocking the path between you and the light source, no photons from that source can reach you. They hit the obstacle and get absorbed or scattered in other directions. You're in shadow, not because light can't reach you, but because something is stopping the photons from reaching you. The photons are still there, still traveling, just not in your direction. But here's what's strange. Light is a wave. Waves can bend around obstacles. Sound bends around corners. You can hear someone talking even if there's a wall between you. Water waves bend around rocks, but light doesn't seem to bend around corners. It travels in straight lines, creates sharp shadows. Why doesn't light behave like other waves? Actually, it does. Light does bend around obstacles, but the wavelength of light is so small, about 1/2 millionth of a meter, that the bending is tiny. You only notice it with very small obstacles or very careful measurements. So light is both a wave and a particle. As a wave, it can interfere, diffract, bend. As a particle, it travels in straight lines, carries discrete energy, gets absorbed or emitted one photon at a time. This bothers people. They want to know, which is it really? Is light a wave or a particle? And the answer is neither, or both. Light is light. It behaves like a wave in some situations and like a particle in others. you can't picture it as either because it's neither. It's something fundamentally different that doesn't have a macro scale analogy. When you try to visualize a photon, you run into trouble. Is it a little ball? No. It's spread out like a wave. Is it a wave? No. It gets absorbed at a single point like a particle. The truth is, we don't have good intuition for what a photon actually is. We have mathematics that describe how photons behave, and those mathematics are incredibly accurate, but we don't have a mental picture. The photon is a quantum object, and quantum objects don't behave like anything in your everyday experience. But here's what we do know for certain. Photons are real. They carry energy and momentum. They can be created when electrons drop to lower energy states in atoms. They can be absorbed when they kick electrons to higher energy states. They travel at the speed of light, exactly the speed of light, no faster and no slower. And they never, ever slow down or stop unless they hit something. A photon in motion stays in motion forever. So when you ask why everything isn't bright, you're asking a deep question about the nature of light and the structure of the universe. The answer involves geometry, absorption, cosmic history, and the expansion of space. Light never dies on its own, but it does get destroyed when it interacts with matter. The universe is full of light, an inconceivable amount of light, but most of it is traveling through regions where you aren't, in directions that miss you, or has been redshifted beyond visibility. Every photon you see is a survivor. It was created somewhere, traveled some distance without hitting anything, and happened to be aimed perfectly at your eye. Think about that next time you look at a star. That photon traveled for years, maybe centuries, through the void. It dodged every dust grain, every atom, every obstacle between that star and you. And then, at the last moment, purely by chance, it hit the tiny aperture of your eye. You caught it. You saw it. And in that moment of absorption, the photon's journey ended. Its energy triggered a chemical reaction in your retina. The photon ceased to exist. But you saw the star. That's what light is. It's not a thing that fades. It's a thing that travels until it stops. And the darkness you see, the dark night sky, the shadows in the corner of your room, that's not the absence of light. It's the absence of photons aimed at you. The light is out there, filling space, traveling forever, waiting to hit something. But most of it misses you, and the universe is arranged in such a way that most of it always will. That's why you can see darkness at all. Not because light dies, but because most light never reaches you in the first place. And here's the final thing that should change how you see the world. Right now, as you read this, you are surrounded by photons. Photons from the sun, from light bulbs, from screens, from every object around you reflecting light. They're passing through the air, through your body, through everything. Most of them miss the tiny receptor in your eye, but some hit, and those are the ones that let you see. You're always immersed in light. You just catch the tiniest fraction of it. The rest goes on, traveling forever, until something stops it. That's the universe, not darkness punctuated by light. Light everywhere, always, and you standing in it, catching only the smallest glimpse.